Okay. If you recall, we have been on the topic petrochemicals. We saw the very first lecture, the geography, the politics and economics behind the petrochemical industry globally and in the national level. In the subsequent lecture, we went to the C1 chemicals and C2 chemicals. And a part of the C2 chemicals and C3 chemicals, we took up in the third lecture on petrochemicals. And we are on to the last lecture today on petrochemicals. That is okay. So are you able to see the slides?
Yes, sir.
Yes, sir.
Changing, confirm. Are you seeing the change?
Yes, sir.
Yes.
Yes,
Okay.
sir.
Welcome to Department of Chemical Engineering, Banastali Vidyapeeth. We are on CHE 305 Chemical Technology Lecture 29. We are on to the red hot industry petrochemicals. Of course, we had a look at the economics and politics behind the petrochemical industry. Then we took up important C1 chemicals, which are methanol, formaldehyde, chloromethane, which include methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. Important C2 chemicals typically include ethylene, ethylene, ethylene oxide, ethanolamine, ethylene glycol, vinyl chloride, ethyl alcohol, trichloroethylene, acetaldehyde, acetic acid, acetic anhydride, vinyl acetate. So C2 is a big chunk. Okay, and then comes the C3 compound. They include isopropanol, acetone, which we have seen, cumene, we have seen, acrylonitrile. Okay, there is a tick mark missing, we have seen. That leaves us with isoprene. Acrylonitrile, we discussed the Sohio process, I remember. Okay, now we are left with isoprene. We start with isoprene. Isoprene has a very interesting structure. It is 2-methyl-1,3-butadiene. CH2 double bond CCH double bond CH2. Right. So you can see that the carbon 1, 2, 3, 4, and the second carbon there is a methyl here because the bond valency of carbon 4, double bond with this carbon, single bond with this, and a single bond CH3. 2-methyl. The double bond is on the first carbon and the third carbon, 1,3-butadiene. So you know the nomenclature, how the chemical is named. The double bond is on first and third carbon, so 1,3-butadiene, and there is a methyl group at the second carbon, so it is 2-methyl-1,3-butadiene. It's a common organic compound with in its pure form, it is a colorless volatile liquid. Isoprene is an unsaturated hydrocarbon. It is produced by many plants and animals, and isoprene polymer are main components of natural rubber. So, you know, there are two varieties of rubber. One is the natural rubber, which grows in the tree, and the synthetic rubber. And natural rubber is a polymer, which is made up of isoprene. Isoprene is a monomer in which polymerization is done. You get isoprene polymer. That is what is the natural rubber, right? So isoprene becomes important because for all preparation of synthetic rubbers, isoprene is looked up. Isoprene is prepared by using propylene and is an important commodity for polymerization reactions and products. Isoprene is manufactured from propylene using 3 consecutive reactions. Remember, isoprene comes under the C3 compound because it is made from propylene. Okay, so the 3 reactions are dimerization, isomerization, and pyrolysis. All 3. Now, first, propylene, you know the formula CH2CH3, propylene dimerizes. Dimerizes means two molecules of propylene combine to form 2-methyl 1-pentene. Okay, this is interesting. Dimerization, right? And isomerization of 2-methyl 1-pentene to 2-methyl 2-pentene. The double bond shifts to an isomer, right? Remember that in the 2-methyl 1-pentene, the double bond is here on the first carbon, and in the 2-methyl 2-pentene, the carbon, the double bond has switched over to the second carbon, isomerization, right? Dimerization, isomerization, and third is pyrolysis of 2-methyl 2-pentene. Pyrolysis is heating in the absence of air, right? So, because in the presence of air, it will become combustion, right? So, heating of 2-methyl 2-pentene pyrolysis gives you isoprene and methane. So, methane is eliminated as a product here. So, three reactions: dimerization, isomerization, pyrolysis. So, the flow sheet we have will incorporate all these things with the necessary details, right? So, the dimerization reaction, catalyst is tripropyl aluminum, and it is a solvent carrier is used that enables the recovery of the catalyst from the product stream, right? The catalyst get carried away in the solvent, which has to be brought back, and operating conditions are 150 to 200 degrees and 200 atmospheres. Now, isomerization. This requires an acid catalyst on a porous carrier. You have already studied isomerization reaction, how it happens in the petroleum refining, remember, right? N-butane to isobutane, isomerization, right? Operating conditions are 150 to 300 and normal pressure condition. Remember, each reaction I am giving the detail to make you understand that they are under different temperature pressure conditions. They are not taking place in the same equipment. Third is pyrolysis. Pyrolysis, see the temperature, 650 to 800 and normal pressure. So you have the process has a dimerization section, isomerization section, and a pyrolysis section. That's it, right? You have the dimerization to begin with, and as you complete the cycle, you go through isomerization and then pyrolysis. So you can see that the dimerization reactor, there is a propylene feedstock, right? And the catalyst, you have seen tripropyl aluminum, right? So the propylene and aluminum is fed, right? And dimerization happens. See the pressure, 200 atmosphere pressure. So compression to 200 atmosphere compressor and goes to the reactor where dimerization takes place. This is a dimerization reaction, right? And what else? From there, it goes to a flash star where the pressure is reduced. See why the right? The subsequent case is at normal pressure. You don't need high pressure, right? So this reaction requires under say close to atmospheric conditions, right? So flash star, and once you flash, the liquid and vapors they separate, right? And you see a new term coming here, Dow-therm. Dow-therm is an important organic chemical which acts as a what do you call heat exchange fluid, right? So down-therm is a very important chemical, which is organic chemical, which is used widely for heat exchange purposes as a heat exchange fluid, right? Remember, I had told you that solvent carrier is used, which gets carried away and it has to be recovered. That is the reason. So the down term brings it back here and it gets recirculated here. Okay. So from here, the vapors, C1, C2, and then the liquid goes to the second column, C3 tar, where propylene is whatever unreacted propylene is separated, which is brought back to the system for what is that mixing for heating and what is this compression. Okay, then from here the product goes to the dimethyl tar, dimerization tar, right? So now this part of it completes the dimerization, and the next stage is your isomerization. Okay, so you get 2-methyl, 1-pentene is separated, and the heavies are taken out, and the 2-methyl pentene goes to the isomerization reactor. So you can see that this part is broadly the dimerization, this part is the isomerization. From the isomer, then the product separation again happens. You get 2-methyl pentene, right? And to remove, I use what is this? Bromic acid, HBr, right? And my 2-methyl pentene comes to the next stage, pyrolysis, right? So where the pyrolysis column, and in the pyrolysis, my product isoprene is got, right? Isoprene is got, and some methane is generated, and the methane goes. Okay. So this is a flow sheet. So what we have discussed here is pretty easy. Dimerization section, the isomerization section, and the pyrolysis section. Okay, so 3 stages. So all 3 integrated, you have the flow sheet. Next comes the very important process technology known as oxo processing. The very important chemical reaction is used for making wide variety of aldehydes, alcohols, and acids. Right. So you see, we are comfortable with making methanol, ethanol, propanol, but I want no butanol, pentanol, octanol. Right. So I want to go higher and higher. Right. So you make, let's say, acetic acid, etc. These are simple ones. But as I want to increase, then I come to the help of oxo processing. Olefin with carbon monoxide and hydrogen forms aldehyde. This is a very special reaction. It is also known as hydroformylation. So oxo processing is a very broad name, but the correct chemistry is hydroformylation. And it also has a dimerization option. If desired, the aldehyde dimerization can be carried out. In that case, 2 molecules of aldehyde react to obtain a higher order aldehyde. We have already seen that how dimerization is put to use here, right? So we put to use dimerization to combine to propylene into 2-methyl-1-pentene. So similar strategy can be adopted for 2 aldehydes to combine to form a larger one, right? 2 molecules of aldehyde react to obtain a higher order aldehyde. In short, oxo processing can be targeted to generate both short chain and long chain aldehyde. I just want dimerization, fine. Then I can go to hydrogenation. When short and long chain aldehydes are subjected to hydrogenation, then one can produce alcohol or an acid. So if I resort to hydrogenation of the aldehyde, I may end up making alcohol or an acid. Oxygenation, and this is an option. When short and long chain aldehydes are subjected to reaction with oxygen or air, the acids can be formed. So you have wide option with oxo processing. The oxo processing can give you short and long chain aldehydes. Short chain means just dimer. Then short and long chain alcohol, short and long chain acid. So you can see how powerful oxo processing is as a chemical reaction, hydroformylation, right? The gases can be converted into these useful products. Various application of these compounds include for making plasticizers, plasticizers for polymerization, reaction, solvent, detergent raw materials, etc. The process will be, we will see the oxo forming using propylene, but we can extend the concept of propylene to butylene or ethylene similarly. Okay, so we look at only using propylene. It's an addition reaction and catalyst, cobalt naphthenate, operating condition, pressure 100 to 400 atmospheres, high pressure, temperature 100 to 200 degrees C. The reaction is exothermic and reaction occurs on a packed bed reactor where the packed bed acts as a surface to deposit the catalyst, that is cobalt, right? And in due course of reaction, the cobalt enters the product stream and therefore needs to be recovered. So cobalt gets carried away and cobalt is a expensive item. So the cobalt which gets carried away, I must bring it back, recover it. Then I have the dimerization. I can use zinc salt, and the operating conditions are high pressure and moderate temperature. Hydrogenation reaction, catalyst is nickel, operating condition 100 atmospheres and 150 degrees C. These are all my options in front of me. I can now stitch a flow sheet the way I want. Look at this hydroformylation. This is a flow sheet. Okay. So you have the propylene. Propylene goes here, and this is a cobalt catalyst. The spelling mistake here, cobalt, right? COBALT. Okay, cobalt catalyst is added, and zinc modifier, that is to improve, enhance the properties of the cobalt catalyst, and carbon monoxide and hydrogen. Remember, the oxo forming is olefin plus carbon monoxide plus hydrogen. This you know is syngas, and you know how to make it. So when syngas reacts with olefin, I get aldehyde. Okay, so from the main reactor, that is the hydroformylation reaction, right? It goes to the dimerization section, right? Where two aldehydes combine to form. See, remember, originally what has happened is the, what is this? Olefin plus carbon monoxide plus hydrogen forms an aldehyde. Now, if I want dimerization, I pick this up, right? So dimerization, right? And then decatalyzation means, why decatalyzation? I told you the cobalt gets carried away. So decatalyzation means removing the product from the catalyst deposit, right? So I get a crude aldehyde and the spent catalyst, right? And the crude aldehyde, and then it goes to a hydrogenation reactor, right? Where is this hydrogenation? Hydrogenation reaction, right? And then I have a series of distillation tasks from which we have not shown it here, but you are familiar about how to draw it. So if I give you, these are all the components present, and given their boiling point, I can put a series of distillation column to recover the product. So I get my light end, heavy end, and the products, and that's it. And dimerization, so you have options. If there is no dimerization, no hydrogenation, then I get butylaldehyde. No dimerization, but hydrogenation, I get butanol. Dimerization, yes. No hydrogenation, I get octyl aldehyde. Dimerization, yes. Hydrogenation, yes. I get octyl alcohols. So you see, the technology allows you to stitch the flow sheet the way you want to make your product. Hydroformylation. So each of these steps is now discussed in detail. I think we have already thrashed it out. It's just a check of going through it. And what else? The zinc modifier is being added, right? The reaction is exothermic. There shall be cooling. So liquid stream obtained offers phase separation is recycled, right? So exothermic means reactor cooling must be done. Cooling may be done by having a cooling jacket or circulating a cold fluid. The product liquid from the reactor is sent to the condenser, right? The liquid product. So we have already discussed this sequence. So let's not read through this. So you could do it from the PPT because I've already explained you the what's happening here. Okay. Then comes your decatalyzation, that is the removal of the catalyst, right? Phase separator is sent to a packed bed where it is mixed along with steam at 180 degrees C. This is the degree 0 has come down, right? And a pressure of 20 atmospheres. At this condition, cobalt will get transferred to the porous carrier as cobalt oxide. So that is how the catalyst removal is done from the carryover, and then hydrogenation and separation network. So we have a whole series of, see the product now combined contains many hydrocarbons which are to be separated one by one. So we have a series of distillation column. Okay, so that is it. Then come propylene oxide. Remember, we studied ethylene oxide, CH2OCH2, the cyclic one. Similar to ethylene oxide. Remember, ethylene oxide was a very important chemical which is used for making many other products. So, like that, can we have a propylene oxide? Oh, yes, why not? But the catalyst is still a problem. I remember ethylene oxide probably used some silver catalyst or something, but that doesn't work in the making of propylene oxide. So the highly reactive chemical used as an intermediate for production of numerous commercial materials. It reacts readily with compounds containing active hydrogen such as alcohols, amines, and acids. Its main derivatives include polyether polyol, propylene glycol, like ethylene glycol, you have propylene glycol ether, but it has many other outlets, right? Consumption of PO is propylene oxide is dominated by its largest end use, that is polyether polyols. They are reacted with an isocyanate to form polyurethane, that is the synthetic foam, right? Polyurethane and end users include flexible foam for the furniture and automotive industries, and rigid foam for appliance and building insulation. Wow, both extreme. And polyols also go into the non-foam application. So mainly they are used for the foam application. They may also go into non-foam such as coating, adhesives, sealant, and elastomers, as well as thermoplastic resins and fibers. So the main method to obtain propylene is by what is known as chlorohydrination followed by epoxidation, right? So we will look at the reaction like this: propylene with HOCl. This is your chlorohydrination, right? Propylene chlorohydrin is got here. So propylene chlorohydrin is produced. This reaction is at about 35 degrees and normal pressure, no catalyst, and 87 to 90% yield could be achieved. The main byproduct is propylene dichloride. So some side reaction, propylene dichloride, 6 to 9%. The next step is the dehydrochlorination of the chlorohydrin with a 5% calcium hydroxide solution. Propylene oxide is purified by steam tripping and then distillation. Byproduct propylene dichloride, it may be purified for use as a solvent or as a feed to the perchloroethylene process. Right. The main disadvantage of chlorohydrination is the waste disposal of calcium chloride that is involved. Then just look at a flow sheet of what we have discussed here. You have chlorine, lime is or caustic, right? Propylene is added, water, we are manufacturing propylene oxide, right? So I use a caustic wash to remove any acid impurities, right? And what else? The chlorohydrin absorber reactor, right? Then it goes, steam is fed, and waste brine is got because circulating a salt solution for heat transfer, and this is a chlorohydrin saponification and flashing, and then the impurities are removed to get your pure product, propylene oxide, right? And the light ends and the heavies get separated. Then come C4 chemicals. C4 chemicals, you have butadiene. Don't get confused with isoprene. Isoprene and butadiene are different. Remember, isoprene was 2-methyl-1,3-butadiene. Okay. So now here, N-butane can be dehydrogenated, meaning liberate hydrogen from N-butane, I form butadiene. Or N-butane may form N-butylene plus hydrogen. So there are two options available, main reaction and side reaction. And the catalyst used is chromium oxide and alumina. Coke deposition is a very important issue. Carbon formation happens, which cannot be prevented, but the reaction is exothermic. Operating conditions are 650 degrees C and 120 to 155 millimeter mercury low pressure. Feedstock is N-butane with some maybe isopentane from refinery process. So you are not actually mixing gasoline, isopentane, but mostly N-butane, it comes buddy with, isopentane. Okay. So you have the starting point here, right? As discussed, the main reaction is taking place, then separation, and then it goes to the, what is this? The tower, right? Then I get two products, the bottom is gone, the top product is taken and recycled back. Right, and here we are using a C4, C5 feed. This is a typical example, right? C4, C5 feed. So basically we have a reactor, separator and recycle. The separation network is extremely complex and involves quenching, absorption, distillation and extractive distillation. First, the feedstock is preheated in a furnace along with unreacted gases that have been recovered in the process using the separator network. After preheating in the furnace to desired temperature, the gases enter the catalytic packed bed reactors loaded with the catalyst. After the species residence time, the product is withdrawn and the feed to the unit is stopped. The product is the product withdraw and stoppage of the feed flow to the reactor and unit is carried out using valves. The coke catalyst, that is carbon deposition on the catalyst, the catalyst with coke deposit, we call it coke deposit. Coke catalyst is subjected to combustion using the what do you call reaction? Which reaction? The coke catalyst, simply burn it, right? And by burning it, you liberate heat also. Okay. Then the preheated air not only removes the coke as CO2, but increases the reactor temperature to 650 degrees C. First, see whether it is required or not. But if you recollect, this reaction requires the heat. Okay. So, in the absorber, naphtha is used as an absorbent to absorb all hydrocarbons except the fuel gas. Right? The absorbent plus hydrocarbon enters the stripper, the removal is done, and unreacted feedstock is recycled. Right? The mixture now enters the fractionator to separate the crude butadiene and the heavy end. The crude butadiene has butadiene and unreacted feedstock, that is N-butane and isopentane. Right? The separation of N-butane, other hydrocarbons with butadiene is one of the difficult separation, and they cannot be separated using ordinary distillation tasks. Therefore, a complicated route of separation optimization is done. Okay, so we have a very distinct azeotropic distillation where we have to use our knack to remove the heat. The crude butadiene is mixed with ammoniated cuprous ammonium acetate solution in a mixer settler. This solution is generated by absorbing ammonia into the fresh cuprous ammonium acetate solution. Then what happens is the ammoniated cuprous ammonium acetate is sent to a mixer settler where the butadiene dissolves in ammoniated solution. The gas from the mixer settler unit is recycled back to mix with the feedstock and enter the preheater. The ammoniated cuprous ammonium acetate is stripped to a separate butadiene, ammonia from the ammonium acetate solution. The regenerated fresh solvent is allowed to absorb ammonia and thereby enter the mixer settler. Okay, so you have the butadiene, so C4, C5 butadiene. This is the C4, C5 is the input. Product butadiene. This is a series of separations. Okay. Of course, the ammonia and butadiene, they enter a fractionator fed with water. A series of separation will remove this component, our butadiene from the alcohol. Okay. But now we have a very interesting question that can be looked at. Why should I do it this way? Why not ethanol as the raw material? Remember, we have been talking that in butadiene, the main reaction is N-butane forming butadiene and hydrogenation, right? So instead of butane, why don't I use ethyl alcohol? Because why not? The ammonia solution is subjected to stripping, separate. That for the purification of the chemicals there. And using ethanol as a raw material, ethanol, can be made into acetaldehyde. No problem. Acetaldehyde and hydrogen. Now, acetaldehyde can react with some more some more ethanol. Ethanol first forms acetaldehyde. Then acetaldehyde react with ethanol to form 1,3-butadiene and water is eliminated. Okay, so that is the reaction. One of the most perspective source for butadiene is production. Butadiene production is ethanol, which can be produced from carbohydrate biomass. You already had a glance of the biomass situation. Of course, when we come to the sugar industry later in the course, we will also see that you have access to more, more to join hands for doing the job. Okay. Ethanol. Right. Concept of butadiene production from ethanol has been already confirmed in industrial scale. The one-step catalytic process is to produce butadiene from ethanol had been developed by S. Lebedev and implemented in industry in the USSR the beginning of the 1920s. Whoa. Later on, the Carbide and Carbon Chemicals Corporation in the USA commercialized a two-stage process featuring acetaldehyde as an intermediate. However, as ethylene production facilities were put in operation, these processes lost their competitiveness, primarily due to high energy costs. Okay, so this always takes time to switch over to a new raw material. Okay, it's not all that easy. Politics and economics come into action there, right? The existing ethanol to butadiene requires substantial improvement for the development of novel catalysts with a high activity and selectivity is of prime importance. However, even today, the concept and the probability of butadiene synthesis from ethanol remain vital and of change. Just look at this ethanol process, simplified, right? So I have my ethanol and biomass being added. This is a recycled one. So ethanol, right? This is your ethanol reactor. Heat is given there, and similarly, the part of the ethanol is there in this ethanol reactor, right? This is a separator from where the purification stream, purification goes to purification, right? And the unreacted material all recycled back. So butadiene can also be made from ethanol by using metal promoted magnesia silicate analysis, silicate catalyst. Okay, so you have a simpler flow diagram here. Butadiene product is got here, right? And aqueous solution is fed here. It goes for hydrogen separation. Okay. Hydrogen separation, then there is a recycle, water separation, C4 separation and product recovery, and unreacted material is recycled back. Then comes the malic anhydride. Malic anhydride, Ma, right, is produced commercially by the oxidation of benzene or butane. Wow. So I take butane and oxidize it, or I take benzene and oxidize it, I'll get malic anhydride. The butane-based process is considered to have superior economic and is preferred route used by from producers as the cost of benzene is high. Malic anhydride can be produced from butane. Malic anhydride, yes, there we are. So, butane-based process, I can use benzene or butane, but benzene is more expensive. So, butane, we settle down, butane-based process is considered to have superior economic and is the preferred route used by most producers as the cost of benzene is high, right? And malic anhydride can be produced, Ma, can be produced from the butane in either fixed bed or fluidized bed reactor processes. The fluidized bed process has advantage over the fixed bed, such as lower air to hydrocarbon concentration, the feedback, and no need for premixing, and but as a disadvantage, abrasion of the catalyst and conversion rates and byproduct formation. These are headaches, right? Malic anhydride is an important intermediate in the chemical industry. It is used in copolymerization. We will look it up in when we do the polymers. See, when the same monomer polymerizes, it is a normal polymer. But if there is a monomer and a copolymer polymerizing, then we end up with what is this? The chemical industry, it is used for copolymerization. Copolymerization means I have polymer and I have another, my monomer and a comonomer. That's what will lead to copolymerization. So how is malic anhydride formed? So look at the structure of malic anhydride. 1, 2, 3, 4, 5. 5 carbon, pentagon type, right? And here it is O. And these are all double bonds. This is known as furon, right? This is furon. Furon gives you malic anhydride, and furon can be got from here C4H6. What is C4H6? C4 butadiene. butadiene, see C4H10 is butane, C4H8 is butene, C4H6 is butadiene. So C4H10 is normal butane, on dehydrogenation becomes butylene, and further dehydrogenation removes to butadiene, and which may form furan, which is an intermediate, and then form malic anhydride. Or my other option is I can use this is the quick representation of a normal butane, right? With 3.5 oxygen can also form my malic anhydride and water. This is a exothermic reaction. So in the fixed bed route, air is mixed with the, this is here, superheated, air is mixed with the superheated butane and fed to the reactor containing the catalyst, which consists of vanadium phosphorus oxide supported on silica, and oxidation is carried at 400 to 430. The reactant gases are cooled and malic anhydride is condensed. Further, malic anhydride is recovered from the malic acid in the water scrubber. So, simple process. And here I have the flow sheet, air, butane. So, this is the process we are using. This is butane and air and butane. And where the two is your fixed bed reactor, one is your air compressor, air is compressed because the high pressure is required, and from the reactor it goes to separator, then it goes to first section 3 is an absorber column, and from there it goes to purification, and then the separation column, light separation and heavy separation. 5 is heavy separation, and 6 is light separation, 7 is your heavy one. Just take 7 is the heavy one, heavy separation. Heavy means higher boiling. Boiling point is raising. As you see, the strategy is remove the lighter one first. That is how we move the sequence of distillation column. Then cooling water and steam is produced. Then comes the big one, aromatics. Aromatics include, benzene, toluene, xylene, BTX. And benzene production using hydrodealkylation route. Toluene does not have much market value. What is toluene? Benzene with a methyl group hanging in one of the corner is what you call as toluene. Toluene has got no market value, right? So toluene is reacted with hydrogen to produce benzene and methane. Wow. So I use toluene to produce benzene. So toluene is reacted with hydrogen. I produce benzene and methane. And main reaction is toluene plus hydrogen. This is an arrow here missing, right? Toluene plus hydrogen form benzene and methane. And the reactor conditions are 600 to 650, 35 to 40 atmospheres. Catalyst is chromia and porous carrier. Other reactions, side reactions happen. Alkyl aromatic plus hydrogen. They also form benzenes and alkanes. Right? Toluene may also form diphenyl and hydrogen. Toluene plus benzene may form methyl diphenyl. Toluene plus hydrogen may form alkane, cracking reaction of the toluene. So we have a whole lot of possibility and headaches. So this is a flow sheet here. I have my alkyl aromatic feed, right? And that, remember, what is this? Aromatics are mostly by dehydrogenation, right? So it goes to the reactor, and from the reactor, this is the products are hot, and the raw material is cold. Raw material is heated and goes with further heating and then brought back to the reactor, right? So, if fresh raw feed is exchanging heat with the hot product. Cold raw material is getting heated by removing heat from the product, right? But of course, startup and shutdown situation will be different. This steady state, right? So you have the compressor here, and then it goes to the gas stripper from where some gases are got, which may be used as fuel, and then it goes to a fractionator where we separate the benzene on top and the heavy end purge at the heavy end at the bottom. The heavy end may be recycled back and small quantities purged, right? And you know the reason for purging. Then comes phenol. I think many of you had picked up phenol for your very first assignment in the course under process alternative. So that makes our job pretty easy to rush through it. Phenol is one of the most important petrochemicals, and it can be made from cumene, toluene, benzene. So all are available to me for making phenol. Phenol, remember, is benzene with OH, all right? So cumene plus air forms cumene hydroperoxide, and cumene hydroperoxide with the H2SO4 form phenol and acetone. Okay, then for peroxidation, aqueous emulsion is prepared using emulsification reaction. Operating conditions are normal temperature and pressure. Emulsification agent is caustic soda, and for hydrolysis, we use 10 to 25% sulfuric acid, and operating condition 55 to 65 degrees C and atmospheric pressure. This is a flow sheet for making phenol from cumene. So cumene and air goes to the reactor, right? We get a whole lot of product there. It goes for sulfuric acid, right? That is the next stage. Sulfuric acid, then separation and a series of purification, and finally we get our product phenol. Okay. So unreacted cumene is removed, must be recycled back, right? And other side products found, methyl styrene, etc., are removed and recycled to the system. Of course, phenol from cumene, similarly phenol from toluene. Toluene and oxygen form benzoic acid and water. Catalyst is cobalt naphthenate. Operating conditions 150 degree and C and 3 atmospheres. Exothermic reaction. Oxidation of benzoic acid to phenol. Benzoic acid plus oxygen. This forms phenol plus carbon dioxide. See, it is not that easy, you know. You have a phenol, benzene, and you just put some water, it will sit and become phenol. No, it has to go through a long step to do this. Okay. First, benzoic acid is formed, right? So the toluene and oxygen, they form benzoic acid and water, and then the benzoic acid with oxygen, then it forms phenol and carbon dioxide. Okay, so the operations are totally different. Now, this is a flow sheet for this process by toluene oxidation. I have my toluene and air go through reactor. Unreacted toluene is recycled back, right? And then my removal and purification of the product. I have some benzoic acid, then again into another catalyst system, right? And series of separation tasks, I get crude phenol, right? From where I move into making the final phenol, right? Phenol can also be manufactured from benzene using several ways. So, phenol has got a whole option. Benzene hydrochlorination to form benzyl chloride, followed by hydrolysis of benzyl chloride to form phenol. Benzene chlorination to form benzyl chloride, right, which is transformed to sodium benzoate and eventually to phenol using caustic soda and HCl. benzene sulfonate process. Using sulfuric acid, I go and for making phenol. So phenol is one of the extensively studied organic chemical where whole lot of chemical reaction have been identified. Okay, but we will quickly look at hydrochlorination and benzene chlorination. So the hydrochlorination route, just see benzene with HCl and oxygen, right? Benzene with HCl and oxygen, you form benzyl chloride and water. Catalyst is ferric chloride and copper chloride. Operating conditions are 250 and atmospheric pressure. Side reaction, benzyl chloride plus water may form phenol and HCl, right? And this is the second reaction, right? The first step, benzyl chloride is formed. Benzyl chloride with water form phenol. Remember, it's so simple. On a benzene ring, we want to put a OH. We can't do it directly. That's the beauty of the benzene chemistry and structure. So I make a benzyl chloride, right? That is, put a chlorine, and then I quietly whack the chlorine and replace it with OH, right? But directly trying to add a OH into benzene doesn't work. Okay, so for this step, the catalyst is silicon oxide. Here HCl is regenerated and will be recycled. Operating condition 350 and at normal pressure. So this is the flow sheet for the chlorination route, hydrochlorination call it, right? Benzene, HCl, oxygen, benzene, where is the process? Just have a look. Benzene, this is the final stage, phenol purification. Water circulation here. Okay, then so here on scrubbing, we remove and where is this crude phenol? Heavy N, spelling mistake there. Hot water, water wash. The catalyst is there. Heavy N, crude phenol is got from where you have a purification step to get the product phenol. Okay. Yes, this is the product phenol. Then the benzene hydrochlorination, this we have seen. Hydrochlorination rule, we have seen this. What is this? This is the flow sheet for hydrochlorination. Then comes from the chlorobenzene route. Benzene with chlorine form monochlorobenzene. Then benzyl chloride with caustic soda form sodium benzoate. Right? And NaOH is in aqueous media. And then the hydrolysis of sodium benzoate with HCl gives you phenol and sodium chloride. So I have my gases here, C6H6, the catalyst, this is the chlorination, and this my product is formed, monochlorobenzene. Then it goes to a neutralizer for causticization and separation here, and the diphenyl is a base product. Where do I get my, yes, the product is there. Next I have styrene. Styrene is yet another aromatic compound, C6H5, CH double bond CH2. That is over a benzene, I am adding a ethyl group. Not ethyl, CH2 double bond CH. Okay, so reaction, alkylation of benzene. So benzene and ethylene react to form, this is ethyl benzene, right? So styrene is nothing but ethyl benzene. So I react benzene with ethylene to get ethyl benzene. Catalyst is aluminum chloride and C2H5Cl, right? Provide hydrogen and chlorine free radicals. Operating conditions are 95 degrees C and 1 atmosphere, and the reaction is exothermic, right? This is ethyl chloride, C2H5Cl, right? Dehydrogenation of ethyl benzene. Ethyl benzene on heating gives you styrene and hydrogen. Reaction is endothermic. Catalyst is SNO or FeO, and operating conditions are 800 degrees C. This is a long flow sheet, right? So this is the manufacture of styrene, which goes step by step everywhere. So from my input there, I put all the sequence, which by now you should be good in developing, right? So read the process and make the sequence, and then come to the dehydrogenation of ethyl benzene. First, you get the ethyl benzene out in the system, right? Yes, dry ethyl benzene is got, and that goes to the next step, dehydrogenation for styrene and hydrogen. Okay. So that is your styrene manufacture. Of course, styrene is one of the most important large volume chemicals. It's mainly used as a monomer for polystyrene, which is used in the manufacture of all sorts of packing material, polystyrene. Other major applications are in ABS, acrylonitrile butadiene styrene, and SBR, styrene butadiene rubber, and other copolymers. Styrene is produced from ethyl benzene by dehydrogenation. Right. So this is your ethyl benzene. By removing a hydrogen, I get my styrene. The benzene dehydrogenation reaction is highly endothermic. This reaction is endothermic and requires a high temperature and low ethyl benzene partial pressure are clearly preferred. Right. See, remember, dehydrogenation means the increase in number of moles, which means the low pressure favors. Okay, so that elementary Lee-Chatter's principle application, you have to keep extending in every reaction. Okay. Most processes for the production of styrene use adiabatic fixed bed reactors. Complete conversion of pure ethyl benzene under adiabatic operation would result in a large temperature drop, kinetic limitation, and the steam ethyl benzene ratio is 12 to 17 mole per mole in order to supply enough heat for the endothermic reaction. So we need to put in steam, and this is the steam ethyl benzene ratio is given here, right? So there is also a reverse flow reactor, reverse flow plug flow reactor, RPFR, right? And what is it? Let's see. Ethyl benzene and steam, it comes out, goes to a separator where I get my crude styrene out, right? And this is my reverse flow reactor, reverse plug flow reactor, RPFR. Plug is missing, add it, reverse plug flow reactor. This is a plug flow reactor. Most of the reactor models are CSTR, continuous third tank based, but plug flow reactors are picking up, and no doubt in the coming time it will be used in this situation, right? So I have my reverse flow plug flow reactor where I keep my ethyl benzene there and steam. My reverse plug flow reactor is there. Okay, so what is this? The crude styrene is separated at this temperature. Then come of some important nitrobenzene. Nitrobenzene is a very important chemical intermediate. More than 95% of nitrobenzene is used in the production of aniline, which is used to make isocyanate for polyurethane foam, plastics and dyes. The process consists of three major sections: benzene nitration, purification and vent treatment. Benzene is preheated and fed to a plug flow nitrator. Nitric acid, benzene nitration is 65% volume by volume, is also preheated and mixed with the fresh and recycled concentrated sulfuric acid and before being fed into the reactor. In the nitrator, benzene reacts with the nitric acid, producing nitrobenzene. The process operates with a stoichiometric excess of benzene to ensure complete nitric acid conversion. Then comes phthalic anhydride. Phthalic anhydride, I think the last of the chemical in our series, C6H4CO2O. Basic raw material is naphthalene or orthoxylene. Naphthalene plus oxygen form phthalic anhydride, water and carbon dioxide. Orthoxylene and oxygen, they form phthalic anhydride and water. And the side reaction produces malic anhydride side product, CO2 and water. Catalyst vanadium pentoxide operating condition 340 to 385. The reaction is highly exothermic, right? So my preferred input is naphthalene or orthoxylene, and heating. I put it into the reactor. Goes to a precipitator and then steam, right? And there's a heat exchanger. From here, the heavier products are removed as tar, and the lighter boiling ones are going to the what is this separation, where we are getting the vent gases. So one product you get here is tar. So this is your phthalic anhydride. So I think that is it. So see, the petrochemical is a ocean. We have just tried to pick up a few of the chemicals that are of fair importance to understand the beauty of the chemistry and the beauty of the reaction. Right. So petrochemical is an interesting field, and I hope you are well informed on the different types of C1, C2, C3, C4, and aromatic chemicals, how they are got, different strategies are used, right? So we will end the lecture there, okay? So coming to, yes, coming to the syllabus for that test, I will just come to it. For today's lecture, I have already uploaded the PPT for petrochemical. Remember, petroleum refining, we had 4 lectures. Petrochemicals, we have had 4 lectures. So, all the PPTs are there in the Google class. Okay. So now coming to the